You know, every time you flip a light switch, you're plugging into one of the most incredible, complex machines ever built. But what you don't see is this frantic, nonstop balancing act happening every single second to keep the whole thing from crashing down. So today, we're going to pull back the curtain on the grid's invisible heartbeat.
And that really gets us to the core mystery, right? We just expect the power to be there. But what is it? What's the secret sauce that stops the entire system from just collapsing any moment of any day? Well, the answer is kind of simple and at the same time mind-blowingly complex.
Okay, it all boils down to this one epic tug of war. On one side, you've got generation. That's all the power plants pushing electricity out onto the grid. And on the other side, you've got demand. That's all of us, flipping on lights, charging our phones, you name it. And here's the golden rule. The one rule you can never ever break. They have to be perfectly matched. Instantly. But here's the catch. Generation is controllable, but demand? It's all over the place. That's the real challenge. So how on earth do grid operators handle this? I mean, how do you manage that chaos? Well, they watch one single number. It's like a vital sign that tells them absolutely everything they need to know about the health of the entire grid. You can think of it as a pulse, a constant, steady heartbeat. And here it is, 50 hertz. At least that's the magic number here in Europe and in a lot of other places around the world. This is it, the steady, rhythmic heartbeat of a healthy, stable power grid. As long as that number stays locked at exactly 50 hertz, everything is okay. The lights stay on. So what even is this frequency? It's not just some abstract number on a screen. It's literally the physical speed of massive turbines spinning in power plants all across the continent. When supply perfectly matches demand, they all spin in sync at a speed that creates a current that alternates 50 times per second. That's 50 hertz. The second that number starts to drift, it's a massive warning sign that the grid is in trouble. The balance is broken. So who's in charge of keeping this perfect rhythm? Well, it's not just one person or one thing. It's this incredibly sophisticated, multi-layered defense system. And these are the guardians of the grid. And this table here lays it out perfectly. The defenses are called ancillary services, and they work in 3 waves. First, you've got primary control. Think of it as the first responder. It's automatic and reacts in under 30 seconds. Then you have secondary control, which kicks in to fully restore the balance over the next few minutes. And finally, there's tertiary control. This one is manual. It's the strategic backup for long-term stability. Let's try an analogy. Imagine you're driving your car with cruise control on. Primary control is like the cruise control, making those tiny, split-second adjustments to keep your speed perfect. Secondary control, well, that's the system automatically giving the engine more gas when you start going up a long hill to keep you at the same speed. And tertiary control? That's you, the driver, seeing a huge mountain ahead and deciding to manually downshift. It's a strategic move to handle a big, long-term challenge. Okay, so that's the theory, but let's really put it to the test. Let's throw a wrench in the works and watch these guardians of the grid actually jump into action during a major event. So here's our scenario. Picture this. A massive factory, maybe steel mill or a data center, is pulling hundreds of megawatts of power from the grid. And then, all of a sudden, they shut everything down. All that electricity that was being generated just for them suddenly has nowhere to go. What do you think happens? Right now, before anything happens, life is good. The grid is in perfect harmony. Generation is perfectly matching demand, and that heartbeat is a rock-solid 50 hertz. The system is happy. And then, click. The factory goes dark. Instantly, the grid is flooded with 200 megawatts of extra power that nobody is using. This is called overgeneration. We now have way more supply than demand, and the whole system is thrown dangerously out of whack. And here's the immediate result. That extra energy floods the system, and it actually messes with the physical speed of all those synchronized generators. The grid's heartbeat stumbles, and the frequency drops to 49.8 hertz. Now, a 0.2 hertz drop, that might not sound like a big deal, right? But in the world of grid operations, this is a 5-alarm fire. If that number drops too far, safety systems will start automatically shutting down power plants to protect them, which can cause a catastrophic chain reaction, a blackout. The system is unstable. And this is the amazing part, the very instant that frequency starts to dip, the guardians are already on it. A fully automatic continent-wide recovery process kicks into high gear to pull the grid back from the brink and get that rhythm back to normal. So first up is primary control. It acts like an emergency brake. In less than 30 seconds, it stabilizes the frequency and stops it from falling any further. It catches the grid. Next, secondary control jumps in. Over the next couple of minutes, it methodically nudges the frequency all the way back up to that magic 50 Hz. And finally, once the immediate danger is over, human operators activate the tertiary reserves. They take over the job from the secondary reserves, which frees them up to be on standby for the next emergency. What's just incredible is that this whole high-stakes drama, the sudden imbalance, the heart-stopping frequency drop, the perfectly choreographed recovery, it all happens completely invisibly. It happens hundreds of times a day, and it's the silent, tireless backbone of our entire modern world. So what's the big takeaway from all this? Well, our grid is kept alive by this non-stop balancing act. That layered defense system, primary, secondary, and tertiary, makes the grid incredibly resilient. And you have to remember, that shaky frequency isn't the problem, it's just the symptom. The real issue is always that imbalance between supply and demand. At the end of the day, keeping that 50 Hz heartbeat steady isn't just some technical goal, it's the very definition of keeping our lights on.
And that leaves us with one last really big thought. This amazing system we've talked about, it was designed for a world of big, predictable, controllable power plants. But now, we're adding more and more renewables, like solar and wind. And while they're fantastic, they're also unpredictable. The sun goes behind a cloud, the wind stops blowing, and the grid's balance gets way harder to maintain. So the billion-dollar question for the future is this. How do these guardians, how does this entire balancing act have to change to keep that heartbeat steady in a whole new world of energy?